Hi, everybody. We are finally starting the chemistry half of physical science, and notice that we're jumping all the way up to chapter 16. The chapters that we are skipping over are kind of specialized physics chapters that, if we have time at the end of the year, we will come back to. But I wanted you to kind of know what we're doing here. And so, as we're starting chemistry, we're going to start with the basics, which means we're going to start with atoms. So first off, models. We're going to use models, of course, because we are studying something that we cannot see. We've talked a little bit about models before. They are simply used to give us a visual, so we can picture an atom even though we can't see it. And so we can kind of know where the parts are and how they're thought to interact. It doesn't mean it's 100% accurate. Like we will color our models, or obviously the size will be different. The shapes, the symbols that we put on them will be different than how they may actually look if we had the ability to see them. So just kind of be aware of that. And again, you guys have studied atoms before. I don't know that necessarily you're going to learn anything new in this chapter, but definitely there will be a review of things that you've covered in the past. Okay, so a little bit of history. As far as atoms go, the first known discussion of atoms was in the 4th century BC. A philosopher named Democritus, he was one of the Greek philosophers, said that eventually we are going to get to a point where, as we get to smaller and smaller parts of things, we will get to something that is indivisible. We can't divide it anymore. And he called this an atomus, and that means indivisible in Greek, and so that's where we get our word atom. As far as how they were held together, he theorized that they were held together by little hooks. That picture that you have, that purple circle, is for the next guy, but and I couldn't find a good picture for Democritus, but I always picture it almost like kind of like Velcro, but not quite. So just have these little hooks that kind of interlock was his idea. So Democritus didn't get a lot of kind of traction with his idea initially. There were some other philosophers who had different ideas on what things were made of, but after a while, a long while, the concepts that Democritus came up with in terms of atoms kind of came back around. And as they did more experiments, as real science began taking place, they found out that he was right, that we do get to a point, or where they thought they got to a point, at least, where they got to indivisible pieces. And based on what Democritus had written, and also some of those early experiments, a man named John Dalton wrote the first atomic theory. And he had 4 main parts to his atomic theory. He said, first of all, that all matter is made up of tiny indivisible particles called atoms, straight from Democritus. His visual of an atom was different than what we know today, but at the time he said that atoms are a solid core and they're surrounded by an envelope of heat. So he kind of pictured them like as really tiny little BBs that were kind of hot. So then his second part, atoms of the same elements are the same. So if I have a handful of gold atoms, then they're identical to each other. And then the next one is always kind of like a, duh. Atoms of different elements are different. So if I had a handful of gold and silver, that'd be awesome. The gold atoms would be different than the silver atoms. And then finally, he said that atoms of different elements will combine in fixed number ratios to form different compounds. This is kind of the easy example of this is water. The chemical formula for water is H2O. And when you have any proportions like that are the same, so here's water, H2O. Sorry, I'm writing with a marker all of a sudden. Wow, how'd that happen? But as long as it's still in that 2 H's to 1 O ratio, it would still be water. So if I had H sorry, I had to do some math there, ch603, still the same ratio, because it's like a fraction. I can still divide it and get back to those original numbers. That's the law of definite proportions. Okay, our next guy. Now I believe this guy was a little bit later, of course, than John Dalton, and his name was J.J. Thomson. I should know the year. I want to say it was like early 1900s, but who knows? I'll talk about it in class once I look it up. Anyway, he discovered that there were negatively charged particles given off by energized metals that were part of the whole atom, and he called these little particles electrons. Now, he concluded that atoms contain positive and negative particles. They were neutral, and so they had to cancel each other out, and then they were held together because positive and negative particles attract each other. This was commonly known as the plum pudding model because it looked like a bowl of pudding with plums in it. The way I colored mine, again, is just because it's a model, and JJ would have said that the red part is the positive charge of an atom, and then each of those blue circles would be an electron. Okay, now before we get to the next guy's model, I want to talk about a man named Ernst Rutherford. He performed one of the most often repeated, most famous experiments ever, and from it came up with pretty much the model that we use today, with a few kind of little tweaks to it. But what he did was he bombarded a metal foil, gold, with alpha particles. Alpha particles are similar to like the radioactive particles that come from the sun, the things that give you a tan. And so it's similar also in a way to like how X-rays work. And so on our picture here, we have our alpha emitter, which is this thing over here. This is what is shooting out these alpha particles. So that darker black line is alpha particles. And then right in the middle we have the metal foil. So this is foil that is basically, or he tried to make it like one atom thick. He rolled it out and rolled it out and rolled it out until he had kind of smoothed it out. And so, you know, we think of aluminum foil, of course, but like see-through, essentially, so thin that it wasn't really, but you know, as thin as he could get it. And so that was in kind of like in the middle of the room, and then on the other side of the foil was a fluorescent screen. And so this is like an X-ray, like an X-ray film. And so what he saw was that most alpha particles went straight through. So that's what the red line is. They didn't hit anything, didn't come close to anything, just went straight on through. Then he saw a few, and the reason he knows is when that alpha particle hits the fluorescent screen, it makes a little like spot of white. So it's a black screen. Wherever these alpha particles hit, you see a little white dot. And so he, you know, was constantly checking where, you know, all the dots were. So like I said, most of them were just straight on through. A few of them went through, but they were kind of deflected off. So like they were going and then they kind of veered off course a little bit, you know, going or you know, kind of veered down, like they were kind of being pushed off course. And then every once in a while, a dot did not appear on the fluorescent screen, like the alpha particle never made it through. And so Rutherford knew a couple of things. He knew that alpha particles were positive. So that's, you know, that charge up there. And he also knew how magnets acted. If you try and bring the two positive ends of two magnets together, you know how they kind of circle around each other. Like you can make them hit if you push hard enough, but for the most part, they'll kind of push each other away. So he theorized, because of the alpha particles, in particular because of those angles that they came off at, that something in the middle of those atoms had a positive charge, so that when the alpha particle came too close to it, it would get that push off course, and then you'd see those angles. And so he said most of them went through because that positive part that is in there is very, very small and it's very dense. And then the ones that didn't go through, the green line in this case, must have had a head-on collision with that positive part of the atom and just bounced straight backwards. Okay, so from all of that, this is what Rutherford's model looked like. So he said very small, dense center that is positive. He called this the nucleus. And he incorporated the electrons that J.J. Thomson had discovered, and he said they're not embedded, it's not like one solid thing, but the electrons are kind of flying around the nucleus, and he described it like bees around a hive. So very, just kind of all over the place, no real pathways. And he said they were pulled close because they're attracted to the positive. The electrons are negative. They're attracted to the positive nucleus, but they can't get too close because of all the other negative electrons pushing them away. So you have kind of this kind of push-pull situation going on here. And he also said that most of the atom is empty space. And so that's the ones that went straight through. Now he did also later call the positive particles protons. So we've discovered, or the positive in the nucleus. So we've got protons and electrons as far as the models go. Okay, so now the next guy, he didn't really come up with a model, but he contributed to the structure. A man named James Chadwick, and he discovered neutrons. And he said that these are particles that don't have a charge. They're approximately the same size as protons, and they are in the nucleus along with those protons. So they're about the same size. Their main job function within the atom basically is to kind of be a buffer so that the protons can all pack together in the nucleus, but without pushing each other away. Okay, so they did all of these, calculations based on Rutherford's experiment, said that the nucleus is about 1/100,000th time as large as the entire atom. So very, very small with lots and lots of space. They had the electrons kind of hanging out there. But it wasn't until the next guy, before they found a real location for the electrons. All right, so this was a guy named Niels Bohr, and he observed that when you heat certain atoms, they give off specific colors. So for example, what we see when we see like a neon sign, that there is neon gas running through the tubes in that sign, and when it is energized with electricity, it glows. And in the case of neon, it's that red color. So then he also discovered that when you look at the color, like look at the tube through a prism, so like a crystal, then you can see different wavelengths. And you guys may remember Roy G. Biv. Roy G. Biv corresponds to the colors of the rainbow, of course, but it mainly corresponds to the energy that is found with those different colors. And those are the wavelengths that we're looking at, or that, that's what our eyes can see as color. And so different colors have different amounts of energy. And Bohr proposed that electrons in an atom, when they are heated up, energized with electricity, they jump to a higher energy level, but it's not really where they're supposed to be. So they have to go back to the original level. When they go back, they give off energy. That energy is what our eyes see as color. And so on the spectrum, red is a lower energy, while the violet end is a higher energy. And from this, he said different atoms have different energy levels. Electrons are in these different energy levels. And so he took kind of the next step as far as the models go. So his doesn't look that exciting anymore, but it should look a little bit more familiar. And Niles went through and did math, and he calculated the distance between the nucleus and where the electrons were, and developed a model that accounted for all those different colors and kind of the distance from the electron pathway to the nucleus and included that in his model. So now in this one, the nucleus is right there in the middle. It's the little red dot. It has a +3 charge because it has 3 protons. And then in a neutral atom, those protons would be canceled out by negative electrons. So there would be 3 electrons also. This sometimes is called the solar system model because of its similar appearance. But it took away from Rutherford's model just kind of the randomness of the electrons. Okay, so now we have since found out past Niels Bohr's levels that they're not nice, neat circles. The orbitals, as they call them now, like where the electrons are have various shapes and configurations to them. Some are very simple, like that red circle, but some are more like kind of almost like a figure 8. Some are like a 4 lobe, and then that last one obviously is much more complex. And so it takes more energy to be in different wavelengths. It kind of determines where they are and what the atom is, and it gives a lot of the characteristics. And so lots of math again has been done to figure this stuff out along with a lot of physics based calculations. But this is kind of our known model of the atom. And if you can visualize it in your head, my PowerPoint won't put them all together for me, but if you put all of those, all the purple, blue, and green together, it is our model of an atom. Okay, so now back to these particles that they've talked about. They're the subatomic particles. They're smaller than an atom. And first off, in the nucleus, we've got the protons and electrons. Sometimes your book calls these nucleons, so I threw that in there. That's not a term I will use, just FYI. Okay, so we've got the proton, positive charge. It has a mass of 1.67 times 10 to the negative 27th kilograms. That's really small. That is 167 with 26 zeros in front of it. So very, very small, but still way bigger than the electron. Protons tell you what the atom is. They determine most of the atom's properties. Neutrons, no charge, the same mass as a proton, and they basically help the nucleus stay together. Then we have the electron cloud, and this is where the electrons are. They have a negative charge. Their mass is 9.11 times 10 to the negative 31st. So that would be 911 with 30 zeros in front of it. And electrons are mainly responsible for how atoms interact with other atoms as far as reactions go. Okay. So now these numbers, first off, I'm going to look at the atomic number. And when you guys are in class when we're doing this, we'll look at the periodic table and talk about some things. I'll give you a periodic table so you can have one kind of labeled in front of you all the time. But first off, atoms are unique because of the number of protons they have. It is how an atom is identified. So, for example, aluminum has 13 protons. If there were one less proton, if I took one away, it would not be aluminum anymore. Excuse me, it would be magnesium. And every time I run across an atom that has 13 protons, that is aluminum. It never changes. So if you've got 13 protons, it is aluminum. And so that number determines the kind of atom. And so it is typically called the atomic number. On our periodic table, it is in the top right corner, and it is basically how the elements are put in order. In a neutral atom, so no charge, equal positive and negative, so equal protons and neutrons, you have equal numbers. I think I just said that. An equal number of protons and electrons. Okay, mass number. The mass number is the number or the total of the protons plus the neutrons. And if you need to calculate neutrons, you just reverse that and you would subtract the mass number minus the atomic number. On our periodic table, the other number in each of the squares is the average atomic mass, and it has to do with isotopes. Isotopes are atoms of the same element, which means they have the same number of protons. So 13 protons means it's aluminum, but they could have different numbers of neutrons. So instead of just having 13 neutrons, they may have 14 neutrons. And so those two atoms, even though they're the same thing, would have different mass numbers because of the different number of neutrons. And the reason on our periodic table that the mass numbers, the atomic weight is what it is labeled as, is a decimal, is because they've averaged what they have found naturally. Okay, so now isotopes. Isotopes typically are written so you know which isotope you are talking about. And so we have isotope notation. And this is a special symbol that shows you the atomic number and the mass number. And so when you're looking at these notations, you always have the letter or the chemical symbol for that element. The bottom number will be the atomic number, and the top number will be the mass number. So notice on this example, you have two atoms. Both of them are phosphorus. That's what the capital P stands for. Both of them have a 15 where the atomic number is, because they are both phosphorus. They are the same atom, but notice that the mass number is different. In this first one, if I did the subtraction, mass number minus protons or atomic number, I have 15 neutrons. But in the second one, I have 31 minus 15, I have 16 neutrons. And that is the difference between those two. Same atom, still both phosphorus, but with different numbers of neutrons. Okay, so now talking about the mass, we use the term AMU often when you're talking about the mass of an atom, atomic mass unit. This is a calculated number, but essentially it is 1/12 of the mass of a carbon atom that has 6 protons and 6 neutrons. And so it's kind of just a way to kind of make the numbers easier. Instead of having to, add up the, whatever I said earlier, the 1.6 something something times 10 to the negative 27th, we just say that's equivalent to 1. And so when you are looking at the periodic table, sulfur is 16 on the periodic table, so it has 16 protons and 16 neutrons. And so when I put those together, add them up, I get 32 AMUs. So 32 is the atomic mass unit. Oh, all right. Okay, so now electron level. So back to where the electrons are. So they are in certain patterns, in certain orbits. And again, with Niles, what he figured out was that the energy that is contained has to do with how far they are from the nucleus. The farther away that an electron is from the nucleus, the more energy it has. The quantum model is all the, the colors and circles and shapes. Those were to represent kind of three-dimensional regions. And the same thing with him, the closer to the nucleus, the lower the energy, and vice versa. And we have found that there can be up to 7 energy levels around a nucleus. It just depends on the number of electrons. And there are certain ways to kind of basically tell everybody where the electrons are. So first of all, you have to know that each energy level has a limit on the number of electrons it can hold. So the first energy level, the one closest to the nucleus, can only hold 2 electrons. The second energy level can hold 8 electrons. The third can hold 18. The fourth can hold 32. And so you gradually fill them up as needed. It doesn't mean they have that many. If they need to fill in those spaces, they do. And then the second one has to do more with the stability of the atom. It's based on what they call the octet rule. And this one says that the maximum number of electrons in the outermost energy level, so the farthest away from the atom, is 8. Once you have 8 electrons in an energy level, then they can go to the next energy level and then come back in and fill in the empty spaces from previous. from the previous levels, which I know sounds very confusing, and we'll do an example. Remember, our whole point here is just to kind of hit the highlights of chemistry. So don't, I'm not going to overwhelm you with this. When you take chemistry again in a couple of years, we'll go into much more detail. But anyway, this process of putting the electrons in the right place is called electron configuration, so that you know where the electrons are. That is very important because it helps you determine the valence electrons. And these are the electrons in the outermost shell. These are very important because they tell you how an atom will bond to something else. Okay, so a simplified version of electron configuration is just to use circles to represent the energy levels, and X's or dots or something like that to represent the electrons. So I'm just going to do the first one. We'll do the others in class. But if we're talking about oxygen, this is O over here. This is oxygen. We have isotope notation, 8 protons, 16 for our mass number, so protons plus neutrons. It is a neutral compound, and that means if I have 6 protons, I have 6 electrons. So if I have 8 protons, I have 8 electrons. And so I have 8 dots or X's that I have to put on my circles. So we just said the first energy level can hold 2 electrons. So I don't know if I can necessarily put these in the right spot. So here's an X. Here's the first electron. Here's the second one. They're both in the first energy level. And then that's 2 of my 8. So then the other 6 go in the other energy level. 1, 2, 3, 4, 5, 6. Typically they're spread out evenly. It's hard to write with your finger. Anyway, we'll do the others in class, but it's as simple as that. Okay, now the second part of chapter 16 has more to do with nuclear radiation. And this has to do with the energy that is given off by unstable atoms. And they're unstable because there's some kind of imbalance usually in their nucleus, and they have to get rid of the extra energy to become stable. And this whole field is studied in nuclear chemistry. And it was actually kind of accidentally discovered by a guy named Henry Becquerel. And he discovered that uranium, which is a rock, caused photofilm to be exposed. So he put the rock samples and like some X-ray film in the same drawer, left them for whoever knows how long. And when he came back, there were a bunch of white dots all over his X-ray film where the rock had exposed that film. And so he said that rock contains a source of energy. And he, along with others, called this radioactivity. Okay, so we have 3 main particles that I want to look at, and they are the alpha, beta, and gamma particles. They are typical radioactive parts that we are exposed to on a fairly regular basis, that the sun emits, that rock sources emit. And so this is just how they kind of group them. And it looks very similar to Rutherford's gold foil experiment, because this was kind of happening at the same time, except you have like this big kind of magnet thing going on back here. So you have this negative plate and this positive plate. The plates in this case are what typically help to kind of guide those particles. And then so this next page will have kind of a chart that breaks down what this whole crazy thing is saying. Okay, so we have these radioactive particles, alpha, beta, gamma. Alpha is what I have there in the red. It's typically written as He, isotope notation with 4-2 mass number and atomic number, similar to a helium nucleus because of its size. Has a positive 2 charge, a mass of approximately 4, and then very low penetration power. So that basically means that it can't get through a lot of different substances. Alpha particles are blocked by like your clothing. It's one of the reasons that you get a tan line when you're out in the sun and you have you end up getting a sleeve tan because of your shirt. So these are not considered super dangerous. You're exposed to them all the time, but they're easy to contain. The next one, beta, is represented by lowercase e because it is similar to an electron. As far as the symbol goes, you have a 0 where the mass is and a -1 where the atomic number would be. This is because it has no mass, so it doesn't have protons or neutrons, is what that is telling you, but it does have that negative charge because of the electron, which is where the E comes from. Very, very small, 1 over 1,836 AMU, so very tiny compared to the alpha. It has a medium penetration power though, so it still can't get through a lot. Like aluminum foil will stop beta particles. Your clothing will still stop it for the most part. So yeah, again, not super duper dangerous. And then the last one is gamma. It's represented by that funny little Greek symbol. It kind of looks like a Y or like an R, even if you wrote it a certain way. 0, 0 for the numbers. It is most like electromagnetic radiation, looks like an X-ray. No charge, no mass. Very much harder to stop than the other two, but you can stop it with several layers of lead. It's the reason they put like that heavy lead kind of blanket apron thing over you, like when you have dental x-rays. They just want the x-rays of your teeth and they don't want to expose the rest of you to radiation, and so it's not unstoppable, but it is it's much smaller than the other two. Okay, so now nuclear decay. So when you have changes in the nucleus, it ends up with this extra energy and it has to give off that energy usually as gamma rays. Those can cause problems to living tissue. That's why you don't want to be exposed to too many x-rays over your lifetime. And it is very often omitted with other radioactive particles like the alpha and the beta. Gamma doesn't affect anything, but alpha decay and beta decay, you can end up with new elements being formed. So this little chemical equation down here at the bottom shows, first of all, that first one, the decay of TH. That is an element called thorium. It is radioactive, and it when it goes through alpha decay, so here's the alpha, the He42, it will also produce a new element, and in this case it is Ra, which is radium, and then here's that gamma over here at the end. Now the reason that we know that it is radium, just looking at this equation, and the reason we could figure it out is because the numbers add up. If you treat the arrow as an equal sign, then the numbers on the top will equal the top number on the other side of the arrow or the equal sign, and same thing with the bottom numbers. So 230 is our number that we're starting with here. That is equal to 4 plus 226. Same thing with the 90 on the bottom. 90 is equal to 2 plus 88. So you can figure out what the other element is. So in our example down there, uranium goes through alpha decay, and it gives off, oh, I left out my plus sign, gives off a new element. So you can figure that out just by knowing what your numbers are. So 238 is equal to 4 plus 230 equals 4, sorry, hard to write. And then, so that's the top number. Then the bottom number is 92 is equal to 2 plus 90. Now, I can figure out the symbol, just by looking at the periodic table. Just so happens that number 90 on the periodic table is TH, is thorium. All right, and so they're pretty easy problems, but they give you an idea of what the result is. Okay, so now getting close to the end here, and that's kind of a long chapter. Nuclear bombardment reactions. What do we do with all of this nuclear chemistry knowledge? Some of the times we try and make energy, which is kind of the big thing. But these bombardment reactions, bombardment means you hit things together. And so when a nucleus is struck with another atomic particle or other nuclei, that's a bombardment reaction. And it very often can produce extraordinarily large amounts of energy. Also, other particles can be given off because of the decays. And so we have two forms of nuclear reactions. First one is fission. Fission is when a nucleus is split into smaller, more stable nuclei, neutrons are in there, energy is released. Sometimes this reaction starts, just one atom being hit by one other particle, but it can become a chain reaction. If more particles fly out and they hit more particles, this is the basis for the first atomic bombs, the ones that we used to end World War II. And so the energy that was released from those bombs exploding is what caused all of the devastation, and massive amounts of energy and lots of radiation, which was probably the worst of it for the people in those two Japanese cities that were targeted. But it ended the war, and that was kind of the result, or the purpose. Excuse me. Today we still have a nuclear weapons program, but we also use nuclear fission in power plants to run electric generators. It's not always popular with the people who live near these generators because there are large amounts of radiation that could be given off if there's a problem, but we do get lots of energy from it. Okay, last but not least, nuclear fission. Fission, I said that wrong. Nuclear fusion. Fusion is when you put two nuclei together. And so this one, you take two smaller nuclei, you put them together to form one larger one. It, first off, releases more energy than fission, so that's a good thing. Second off, it uses a fairly stable starting source, which is hydrogen. Not very radioactive, as far as the waste goes. It's like alpha and beta particles. It is what is going on in the sun. The sun is a big, giant gas ball, and that contains hydrogen and helium. Helium is the result of two hydrogen atoms being fused together. That fusion, lots of energy. We get the warmth from the sun. We get the light from the sun. We do get the alpha beta, that's why we get a tan from the sun. Extremely powerful, and we have worked on different forms of fusion, and we can do some fusion, but it's one of those that it's hard to control. The conditions have to be just right, and so it's not, we don't use it like we do fission. Part of the problem is that you have to have really high temperatures, like 50 to 100 million Kelvin. Matter has to be in a plasma state, which is not easy to control, or to come up with those conditions. And then it also needs very strong magnetic fields or magnetic bottles to contain the plasma once you kind of get it started. So fusion, really great. We're still working on it. But anyway, all of this, the reason it's all in chapter 16 is because it all relates to the atom. Whether nucleus, protons, neutrons, or around the nucleus and the electrons. Whew, okay, lots to talk about. Anyway, hope you like it.